All right, okay, so for this second session, so for the second session, the goal is to look at neutrino structure formation on nonlinear scales, right? So this is a slice from one of our largest simulations. The point of this picture of a slice is that neutrinos are a small perturbation to structure formation, right? They're a small part of the dark matter. So in order to simulate structure formation with neutrinos, you must first be able to simulate structure formation without neutrinos, right? So there's a whole sort of weeks-long lecture about how to simulate cold dark matter, which I am not going to talk about. Okay, we assume that that is a solved problem and has been done already. Okay, and we're just going to talk about how you add neutrinos to an n-body simulation. So you might, this is made easier because they are a small component, right? So some things that you might think wouldn't work at all actually work reasonably well. So the most simple thing that you can imagine is to say, okay, these guys do not cluster. Let's just assume that they really don't cluster, right? Let's assume that neutrinos, they affect the background expansion, but their perturbations are zero, like lambda. So then you run an n-body simulation where the total mass in the simulation is like the cold dark matter mass, but the background is the cold dark matter mass plus the neutrino mass. This is obviously going to be wrong on large scales, right? Like the whole deal here is that on scales larger than the free streaming length, neutrinos do cluster. And so running a simulation that assumes that they don't is not going to be correct, right? Nevertheless, if you want to work out something like how the abundance of galaxy clusters or how the abundance of the Milky Way size halos is affected by the mass of the neutrino, this is going to work reasonably well. It turns out that the suppression due to neutrinos is about doubled by this because they will turn out to cluster just a little bit. But I mentioned this because in the back of your mind, when I'm talking about the more sophisticated schemes, think about how they reduce to this, which is the most basic thing, right? Just assume they do not cluster, run your n-body simulation as normal. Okay. The second trick is to assume that the neutrino power is linear power. So we can construct a matter power spectrum by taking some nonlinear CDM power spectrum from the simulation. So this is some 2-point correlation function of a dark matter density field like this. We find this, we take its power spectrum, and then we add in the linear theory prediction for neutrinos, which is this one. And we get a total matter power, and we get a total matter power spectrum. So this is very simple because you're not doing any neutrino-related computation at all, except for the one in class that you already just did 15 minutes ago. This works quite well on linear scales, right? So anytime you're in a regime where k is less than 0.1 h per megaparsec, all the power is well described by linear theory. And so this is going to work really well, right? On those scales, the nonlinear CDM power spectrum is the same as the linear power spectrum, right? So all of these, this is exactly the neutrino power spectrum, this is exactly the CDM power spectrum, and this is exactly the matter power spectrum, and everything's fine, right? However, of course, there will be no point running a simulation if those were the only scales you were interested in, right? The whole point of running simulations, we care about nonlinear growth. So on smaller scales, it turns out that this is not right? So the cold dark matter power, the nonlinear cold dark matter power spectra is substantially greater than the linear cold dark matter power spectra, maybe by a factor of about 10 to 100. So this is doing this on small scales below the free streaming length is equivalent to this one. It's equivalent to assuming that neutrinos cluster above the free streaming length and cluster not at all below the free streaming length. So this will roughly double the suppression in the power spectrum on nonlinear scales that you get due to neutrinos. So this is not quite right. So at this point, if you were working on this, you'd say, okay, well, this is great, but all these perturbation theory guys, they're leading me astray, and I'm a simulator. So as a simulator, I know how to simulate n-body particles. So that's what I'm going to do, right? So I have a technique for simulating cold dark matter. It's the N-body technique. I chop up the fluid, the cosmological fluid into initial chunks, and I evolve the chunks as if they were a single particle using the N-body approximation. Let's just do the same thing for neutrinos, right? So this is an image of an evolved cold dark matter simulation, and this is the evolved neutrino simulation. You will notice the scale here, right? So this is an overdensity, and it goes up to about 100. This is an overdensity, and it goes up to about 2, right? So the overdensities in the cold dark matter are substantially greater than the overdensities in the neutrinos, because, of course, the cold dark matter is able to form these tight, dense halos, and the neutrinos just aren't, right? So this seems like a sensible thing to do, right? How do we make neutrino particles? Well, it's easy. They cluster under gravity, just like N-body particles, right? So the same tricks that we use for evolving gravity for doing cold dark matter, we can use it for neutrinos. However, they have an initial thermal velocity, right? So everything that is neutrino about them is done in the initial conditions. There are no extra forces on them, right? It's not like they have like pressure. They're not gas. They do not interact electromagnetically. They are weakly interacting massive particles. So we do everything that we would do for cold dark matter, but the neutrino particles are zipping around with some initially thermal velocity. Does this make sense? Any questions about that? Yeah, okay. So this sounds like it should work, but there is a problem. So the problem is that when you initialize these simulations, you generally will place particles on a regular grid, right? So you will have an irregular grid of particles. You're taking your density field and chopping it up into regular chunks and moving the regular chunks around. The regular chunks are slightly displaced initially, and that sets the initial power. The neutrino chunks, they are displaced initially, but a very small amount, right? Because neutrinos do not cluster very much initially, right? They're deep within the free streaming length. But they have this huge thermal velocity, which you would naturally think to say is some large random velocity. So let's say you initialized your simulations at redshift of 100, right? A redshift 0 neutrino velocity is 150 kilometers per second. A redshift of 100, it is 15,000 kilometers per second. That is quite large, right? So your box size is finite. Here it's 100 megaparsecs. If you work out how far a particle moving at 15,000 kilometers per second travels in a Hubble time, it is more than 100 megaparsecs, right? So your neutrino particle is going to kind of start here and then zip around your box periodically and end up in some random position, right? So your carefully set up initial grid will immediately disappear. Everything will just mix rapidly, and you will have a randomly distributed set of neutrino particles moving in a gravitational potential set by the cold dark matter. Right? So we're interested in power spectra. So what does this look like in Fourier space? Anyone want to tell me what a regular grid looks like in Fourier space? I think at the back there, someone maybe. No, okay. Someone made a gesture. It is a delta function, right? If you take a regular grid and you do a Fourier transform, you'll get a delta function at the spacing of the regular grid, right? So if you look at the power spectrum, and we'll do this in a minute, of any simulation, you will always see this feature at the spacing, the initial grid spacing of the initial particles. On the other hand, if you have a set of particles that are distributed randomly, your Fourier transform is a white noise power spectrum, which is constant and has an amplitude of 1 over n, where n is the number of particles, right? So you might think, why does this matter? Like, we have this feature from the grid, right? This is a particle feature. Why is the neutrino particle feature worse than the grid particle feature, right? The answer is the delta function is local in k-space. So you just stop paying attention to your power spectrum before you get to the grid scale. You just kind of cut it off your plots, well, okay, I don't want to skip ahead, but look at this. Do you see a grid feature on this plot? No, because I cut it off, right? I'm just not showing it. It's kind of over here somewhere, right? There'll be a delta function, right? But when you have a random set of particles, this 1/n shot noise is on all scales, right? There's no way you can just like throw away the small scales. Every single scale has this 1/n shot noise. And what is worse, so the neutrinos have this simulated power spectrum, which is the true power spectrum plus 1/n. Because they do not cluster, unless n is very, very large, the shot noise will dominate over the true power, and you're not going to be resolving the dynamics properly, right? And this turns out to mess with the answer. Yeah, so this is shot noise, right? So if you are a simulator, this is annoying. You can make it work because this is the number of particles. So you say, okay, no problem, I've got this. I'm going to increase n to a point where 1/n is less than the true power spectrum for neutrinos, and then I'm good, right? But that gets very expensive, right? Then I have to have 8 times as many particles of neutrinos as I had for cold dark matter. And that's very expensive. And it's also kind of a waste of time because they don't cluster, right? Like, why are you wasting like 10 times the, if your neutrino particles are only 1/10 of the total particles in your simulation, but they're the ones doing all the interesting dynamics, like, what's the point? That doesn't make sense, right? You don't want to do that. So since this was realized maybe 10, 15 years ago, people have been coming up with clever ways to fix this problem, clever ways to reduce the shot noise. Yeah, okay, so actually let me show you this. So this is the nonlinear suppression, right? So this dashed line is the linear theory suppression, and this is the nonlinear suppression, right? So you'll notice that it gets larger and then smaller again. It has this distinctive, I like to call it a spoon shape, but a referee once told me off for calling it a spoon shape in the paper and said that it's technically a pre-virialization feature, which sounds a lot better. But it looks like a spoon to me. So it has this spoon shape. There is actually a fairly simple and intuitive reason why it's a spoon, right? So does anyone want to guess why? Okay, so it increases first, right? The nonlinear suppression is larger than the linear suppression, right? And that's simply because nonlinear growth is more than linear growth, right? So it's this is like the trick. This is like your 401k, right? So bear with me. This is like your 401k, okay? So let's say that you, as a grad student, have no money, right? You cannot put any into your 401k because you don't have it, right? Let's say that your friend, who is not a grad student, who works in, like, I don't know, let's say they work for, I don't know, NVIDIA or something. They work for like some company. They have money, right? And they put some of it in their 401k, right? And so they're better off than you. That is the linear theory result, right? However, it's worse than that because not only do they get the money they put in the 401k, they also get the interest on that money in the 401k. So you are foregoing not only the money you didn't put in your 401k because you don't have it, but also the interest on that money. That is what this is, right? So this is the linear growth suppression, and this is the extra nonlinear growth that would have resulted from that linear growth that isn't there to grow, right? So this is your friend's money, and this is the interest on your friend's money, okay? And the only solution is for you to, well, no, okay, if you graduate and become a professor, then you will always be less well off compared to your friend. So there's no solution. Yeah, sorry. Okay, so this is why you get a suppression here. Then on small scales, the suppression goes away, right? So why does the suppression go away? The answer is, I actually can make this now. I was going to say I can't make it. Actually, I can. Okay. So why does the suppression like reduce on small scales, right? So once something virializes, it is virialized, right? If a Milky Way, once a Milky Way halo virializes, it stops growing. It decouples from the Hubble flow, right? It stops growing like a cosmological growth. It is a virialized halo. It kind of stops, right? Like the Milky Way is not really continuously contracting anymore, right? It's just kind of there. So when everything is virialized, when the power spectrum is sensitive to the internal dynamics of a large halo, it forgets what the initial conditions were, right? Like something that collapses has collapsed, right? Like it is a collapsed halo. It'll keep going until it collapses and then it will stop. If it collapses at redshift 2 or a redshift 1 or a redshift 3, it doesn't really matter that much, right? It is still a collapsed halo. So that is why the suppression reduces again, right? Because everything is virialized down on these scales. Related to my analogy earlier, once you reach a certain wealth, you retire. And at that point, people cease being better off or worse off because they've reached their wealth and they've retired and live a life of leisure, okay? And that's what this is like, okay? So the virialized halo is like the person that has enough in their 401k to retire and move somewhere and not do any work anymore, okay? Make sense? Any questions? That's the pre-visualization feature. Yeah. I hope no one was too traumatized by the analogy to your friends at NVIDIA. Okay, so you will notice that, okay, I have a converged particle. So here on this plot, I have a bunch of different simulation methods, right? So I have the particle technique. This gray line is with the same number of particles as cold dark matter, same number of neutrino particles as cold dark matter particles. And you can see that it doesn't quite match linear theory on large scales. That is the effect of the shot noise, right? That's the shot noise messing things up. This red line is a converged particle simulation, and it does agree with linear theory somewhat better on large scales, and that is because it is converged. There are also these other simulations, and you might have gathered from what I said a few minutes ago that these simulations are there because they're a technique to make this work without having a ton of time wasted on a bunch of neutrino particles. So this is the technique. This is the linear response technique. I have claimed that it is very good. There are better techniques, but this one is sufficient, I think. The way it happens, the reason it exists is because I once gave a talk. I was a new postdoc and I gave a talk about like these particle techniques. And I said, this is very hard because there's shot noise and it's a real pain. And Yassine Ali Hamoud was in the audience and he stuck his hand up and he says, this is silly. Why are you doing this? This is ridiculous. Just use perturbation theory for it. Just use perturbation theory. It'll work much better. And I said, that's a very good idea. Let's write the paper. And we did. And this is what this is. So the point of this story is that if someone asks you like an annoying question, you can tell them to shut up, or you can just say, that's a great idea. Let's write a paper. And then it's on them to do the work. And which he did. The way this works is that this is a linear theory perturbative response to a nonlinear input potential, right? So I told you, like last time, I said that I had this beautiful image, and I said all the structure in this image is coming because the neutrinos are responding to the gravitational potential of the dark matter, right? So we can use that because they are responding to the gravitational potential of the dark matter in a linear way, right? Like this delta nu over nu is barely higher than 1, right? And that tells us that we can use perturbation theory to understand how they respond to the gravitational potential of the cold dark matter. The gravitational potential of the cold dark matter is itself highly nonlinear and very overdense, but that doesn't matter because we have an n-body simulation to simulate that, right? So this is a hybrid method. We have an n-body simulation that gives us, at every point in time, the cold dark matter power spectrum. And I literally just compute the cold dark matter power spectrum every time step and save it to an array. And then every time I need the neutrino time step, the neutrino power, the neutrino power spectrum, I pull out this list of cold dark matter power spectra, and I do this integral with some function, some kernel function, and I do the integral over time, and I multiply by some unit function, and then boom, I get the neutrino power spectrum, right? So this works well because the neutrino overdensity is less than 1, and we have the nonlinear cold dark matter thing. So what we're doing here is we are using the ability of the simulation to know what the dark matter is doing, okay? You might say, why are you building this into the simulation at all, right? If it's perturbative, why don't you just do this in post-processing? And the answer is that the future time step for the cold dark matter will feel the total gravitational potential, right? The cold dark matter evolves not in the cold dark matter gravitational potential, but in the total matter gravitational potential. So the cold dark matter needs to know what the potential is from the neutrinos in order to know how it clusters next time step, right? So we need to put this into the simulation. So every single time step, we work out the total gravitational potential. We add this term to the potential from the cold dark matter that's coming from the particles, and then we evolve it a little bit time step forward, all right? It's neat, right? And this is no work, right? You know, we're already doing CDM, and then we do like one integral per time step, which is completely free, okay? And this is this blue line here, and you can see that it agrees with the red line absolutely perfectly because it gives exactly the right suppression of the cold dark matter. One thing it doesn't, you know, there is one caveat that I should mention, which is that I lied just a little bit, just a little tiny bit earlier. So when I said that the neutrino is free stream, right, a medium velocity neutrino free streams, in reality, there is a velocity distribution. It's a Fermi-Dirac distribution because they're fermions. And the Fermi-Dirac distribution has a tail of particles that are moving extremely slowly. Those particles start to behave really like cold dark matter much earlier than you would expect. And for this reason, they start to cluster. So because this linear response technique is perturbative, it kind of forgets about them and so it underestimates the neutrino clustering. They're a seriously small fraction of the total matter, so it doesn't affect the total gravitational potential too much. But you know, there are other ways to do it. Does any questions on this linear response method? Okay. So I kind of am happy with the linear response method because what we observe is this thing on the right here. But it is true that as a matter of you know, sort of crossing every T and dotting every I and being really like serious about getting everything right in cosmology, we should be modeling, you know, we should have a way of modeling all components of the universe correctly, right? We cannot observe the neutrino background, but maybe one day we will, and we want to know what its anisotropies are, you know? Plus, it's kind of fun. So people come up with better techniques than the linear response, specifically to get this right. I want to call out the technique of Arka Banerjee with this paper, not necessarily because it's more accurate than others, but because it is more clever than any other technique. And the way it works is to say that, okay, so this is the Fermi-Dirac distribution. The reason the shot noise is coming around is because we are assigning a velocity at random to each neutrino particle. So instead of assigning velocities at random, instead of like taking a neutrino particle and drawing a random velocity from the Fermi-Dirac distribution, let's draw the velocities in a correlated way, right? Let's make these velocities so that they get sampled in clever shells so they are coherent. And then because instead of each particle moving in a random direction, they're moving coherently, we will still have the same overall velocity distribution, but the coherent shells will move in different, you know, will not randomly jump to a different particle of the box, different part of the box. They will jump coherently to a different part of the box, right? And this is what this does, and it is very clever, and it works quite well. There are also other hybrid methods that combine perturbation and perturbation theory and use particles for the slower neutrinos and the nonlinear parts. I don't have time to talk about them. Generally, they will avoid the shot noise by doing something clever. They will only require a few neutrino particles, and they will be a bit more complicated to implement. Let us now, okay, so yeah, let us now see some results from this. So those of you who are paying a lot of attention, you might have noticed that the initial program for this section said run your own neutrino simulation. I changed that because I thought it was going to be too hard. So if you are running Linux, if you have a Linux laptop in front of you, you are welcome to execute these commands on your Linux laptop, and then you should, in principle, get a neutrino simulation running, okay? The only problem is that if you are running Mac, you need to have all of these packages installed, and it's kind of tricky. And I had this great idea when I told Dragon my schedule. I said, okay, I'm going to figure out a way to not require you to install these by just mocking up a version of my code which needs MPI that relies on some fake MPI, some like very simple MPI for a single processor. And I asked Claude to generate such an MPI library, and it did, and it compiled, and it ran, and it was beautiful, and I looked at the results, and they were completely wrong in every way. So for this reason, rather than try and debug the code that Claude made, I'm going to tell you that if you want to run a neutrino simulation of your own, you can get a Linux and do this, okay? And that's fine. And if you're running a Mac, I'm sorry, you know? See, I used to be kind of a free software absolutist when I was young, and this is the remnants of it, that the code doesn't work on Mac. Or it does work on Mac, but you have to install all these packages, which is hard. So we're not going to run a neutrino simulation unless you're feeling particularly dedicated, but here is one that I made earlier. So if you go back to our Python notebook, you can clone a bunch of power spectra from an earlier simulation I ran. And we can do this. So, okay, so what I've got here, I think I've got like 10 minutes. How long have I got? Oh, I'm actually ahead, yeah. You should ask me questions. Okay, so I have here a redshift 0 power spectrum from a simulation with a neutrino mass of 0.4 eV, right? This is the same cosmology that we used before when we were looking at linear theory neutrinos. And then I have this power spectrum with massless neutrinos, and I have loaded them carefully, and I've plotted them, right? So the dashed lines are the linear theory power that we had, and the solid lines are the power spectrum from the simulation. And what you should hopefully be able to see is they agree approximately on large scales. And then on small scales, the growth is much, much larger, right? So, you know, again, this is the interest, right? This extra growth here is the interest. You see here, I have this time left on this. Do you remember what this was? It's the grid, right? This is the feature of the grid, right? The mean interparticle spacing is like around here. If I were to plot it further, it would kind of go up and then drop, and there'd be like a harmonic function at 1 and 2 and 4 times the grid scale. There's also something kind of going on here. Anyone want to guess what this is? Right, there's all this like nonsense. It looks kind of messy. That's not good, right? So what's going on here? So I haven't rebinned this power spectrum, right? This is just the raw power spectrum from the simulation. The k-bins are really, really tiny, right? So the simulation is a 3D grid. What this is doing is working out the Fourier space overdensity on a 3D grid. Each grid point has a different k, and the number of modes per k-bin is relatively small. So this is cosmic variance, basically, right? Like each k mode has like, each k-bin has maybe 3 modes in. There's scatter on the modes just based on the fact that, oh, this one has a big halo. This one has no, this bit has no halos at all. This one has a big halo. So some of them are low, some of them are high, right? So there are not enough modes per bin. This is sample variance. The way to get around this is to rebin the power spectrum so that each bin has the same number of modes, which is what I've done here. So this has at least 20 modes per bin, and ideally about 200 modes per bin. And I do that. And wow, it looks so much nicer now, doesn't it? Right? So we still have some disagreement on large scales, right? So if you look here, this kind of large scale is not really tracing linear theory, right? Anyone want to guess why that is? So this is the scale of the simulation box. And then close to the scale of the simulation box, there is cosmic variance, right? there's only so many modes in the box, right? You only have this many. If the box is like this, there's one mode here, there's one mode here, and there's one mode here. And then there's the reverse of it, so there's 6. 6 modes, what is the Poisson error on 6 modes? It's 1 over square root of 6. That's kind of big. So on large scales, the simulation box will not trace linear theory particularly well. But on smaller scales, we can get many modes per bin. And it should match linear theory. And then as we go further down, you can see the gap between these 2 lines widens and then shrinks. And I can replot this one. And that shows you, right? So look, it doesn't quite match linear theory on the larger scales. If I plotted the redshift 1 output, it would have done. And that's the cosmic variance. And then it gets bigger. This is the interest lost. And then here, everything's virialized and it starts to kind of come back again. And then this little feature here, this is smaller than the grid feature here, just because we're taking the ratio, right? So a delta function is kind of almost the same in both simulation boxes. It's not affected by the mass of the neutrino, but it's not quite. So this is why we get a feature there. Okay. All right, makes sense. Any questions on this? Actually, I've got 9 minutes. I had like one more thing to say. Let me say it, and then there will be like 5 minutes left, and then you will feel under pressure to ask me something, right? Because otherwise you'll have to go to break early, and that will be a terrible, terrible problem. So here is the neutrino power, right? So what I've done here is I've loaded the neutrino power spectrum, and I've loaded the cold dark matter power spectrum, and here's the cold dark matter, and here is the neutrinos, right? And you can see that the suppression is huge, right? The amount that these things cluster compared to cold dark matter is absolutely nothing, right? Like you can see why the fact that we didn't really get this right is not really important for the total gravitational potential, right? Because this is suppressed by a factor of 10 to the 6, right? So yeah, this bit is wrong by a factor of 10, but even so, if it were 10 times larger, it would still be suppressed by a factor of 10 to the 5, right? So it's okay. Yeah. Any questions? Yeah, you were first.
Thank you for the very nice talk. So as you said, the linear response theory works really well up to some scale. And then you get into virialized halos, and there are these slow-moving neutrinos, which is not properly captured by that theory. So, just thinking in terms of linear theory and then going to small scales, people can stitch that to halo model-like thing. Yeah. And something like that be done in this case with the slow-moving neutrinos?
Yes, you could, I think. I think you could probably stitch it to a halo model. It will be slightly tricky to do because the halo model is real space and the perturbation theory is in Fourier space, right? So what we actually do for the hybrid techniques is we just, instead of, at some point in the perturbation theory, we've integrated out over this Fermi-Dirac distribution. And we just, instead of integrating as from p of 0 to infinity, we integrate of p from some small number to infinity. And then the bit between 0 and some small number is followed by particles, which is similar really to what you said. Yeah. Who was next?
Hi. Hi. All right. So the goal of this is to compare this to observed matter distributions, right? So the neutrinos are about 0.5% of the dark matter. So
sorry, 0.5% of the total matter. So maybe a bit more of the dark matter, because the dark matter is only 1/3. Yeah.
So is it a problem that there's no baryons, because those are a much larger percentage than neutrinos, right?
Right. So in this simulation, there are no baryons, right? So you might say this, but wait, what about baryons, right? That's the question, basically, right? What about baryons, right? So baryons are, of course, quite important, because without them, we wouldn't be here. So you should run a simulation with baryons and with neutrinos in. And then you have to worry about what happens. The baryons are known to affect the power spectrum on small scales because of HM feedback. There are ways, I will talk tomorrow about the Lyman alpha forest, which provides a way to get around that.
Cool.
Yeah.
Thanks.
Some will get around that.
Thanks. At what scales would you expect astrophysical neutrino production to make a significant impact on the, I guess, cosmological neutrino power spectrum?
Where are you? Can you raise your hand?
I'm right over here.
Whoa.
Right here.
Oh, right
Yeah,
there. Okay,
sorry.
great. Yes. Okay, sorry. Yes. I would say very small scales because they are. Yeah, I would say small scales because they're galactic production, right? They have to be in the galactic disk. I'm trying to think how far they propagate, actually. Yeah, you want, the high energy neutrino, that's a good question. I actually don't know the answer. So the high energy neutrinos that come from the sun or from a supernova do interact more strongly, which is why we can detect them, right? So I guess they probably do propagate outside the halo, in which case they should be kind of relevant a little bit, because they should be going around since star formation happened, which would be, I think probably the answer is that their total contribution to omega nu is quite low, right? Because omega star is like 10 to the minus 2, and the amount of stellar material that ends up being in neutrinos is going to be quite lower than that. So they're probably going to be like less than 10 to the minus 5 or so of the background. They probably are quite highly clustered. Yeah, it would be kind of an amusing project to like work out what the map of high energy neutrinos would look like on the sky. Probably someone in IceCube has done it. Yeah, anyway, good question.
I have a question going back to the first portion of today's lecture where we were looking at the plots of the power spectrum kind of at different redshifts, and we were talking about the suppression kind of evolving through cosmic history.
Actually, that was
This that
one,
plot, yes.
Yeah.
So my eye was kind of drawn to the feature where around 10 to the minus 2, like Fourier scale, there's kind of this crossover between kind of more power for more recent redshifts versus more power for older redshifts. Is that just kind of an artifact of the plot, or does it have anything to do with, for example, the turnover scale of the matter power spectrum?
It would be, so here I have plotted the ratio of the matter power spectrum, and here I have plotted the ratio of the cold up matter baryon power spectrum, excluding neutrinos. It's less visible in this one. So to some extent, it is an artifact of the way I'm plotting this. But, well, I want to say it has something to do with the fact that dark energy domination happens between redshift 0 and redshift 1, right? Because it's a crossover between, if you look carefully, the redshift 1 and 2 power spectra kind of are closer to the redshift 9 power spectra, but more suppressed, and the crossover only happens at redshift 0. So I would say this is because this increase is due to dark energy domination, and I want to say the ISW effect. Yeah, I think that would be my answer. It's not the turnover, but it is cosmological. Yeah. I might be wrong about that, actually. Am I right about that, or am I wrong about that?
The question is, why don't these curves go to 1 on the left side?
Yeah, well, that I did tell you the answer, right? Because that's the background effect, right? So the background's a little bit different, I think.
I think we are close to finishing
We're
this
exactly
session.
3:30.
And there are actually more questions in the Slack. If you
Oh, there are.
can
I will
take time during the day to answer the questions, would be good.
I will do that.
So
Thank you very much.
Let's thank the speaker again. Let's have 30 minutes break.